Hello, in this video you will see three very important formulas with a proof that they are really valid and with geometrical illustrations. Let's start. Three important formulas with geometrical illustrations. And here are the formulas. They are known as the square of a sum, the square of a difference, and the difference of two squares. They are also called many interesting names in different languages. The nicest one is probably the remarkable identity, because, well, these identities really are remarkable because they are very simple and still they are very, very important and have a lot of interesting applications. And now I will start by simply proving that they are true, so that you can feel confident using them. And I will prove them just by going from the left-hand side to the right-hand side and showing that I get the same result. So I start in the first formula from a plus b all squared. You know that squaring means multiplying the same number twice with each other. So it is simply equal to a plus b times a plus b. And you remember we have proven the formula for a product of two sums in the previous video. So now I know exactly how to do this. I know that I have to perform my multiplication in this way and here later in this way. And this will give me first a times a is a squared, then a times b is ab, and then I continue with ba plus b times b is b squared. And you see I have ab and ba, but it's the same, right? Because multiplication is commutative, does not depend on the order of your the factors. So I really get a squared plus twice ab plus b squared, which is exactly the right-hand side of the formula. In exactly the same way I can prove the second one. The difference is that I have differences in play instead of sums. But the rule is exactly the same. So first I have to multiply a with both elements in the second parenthesis and then minus b. And maybe you wonder why I say that it's the same formula. Well, remember that minus a is the same as plus minus a. So subtraction is just addition of opposite number, right? So here I first get a times a is equal to a squared. Then I have a times minus b. I will write it like this, a times minus b. And then I continue with minus b times a, so plus minus b times a, and then plus minus b times minus b, right? And now I can rewrite it in the following way. A times minus b is equal to minus ab, right? Minus ab. Then minus b times a is equal to minus ba, which is minus ab, right? Because again, multiplication is commutative. So I get minus ab one more time. And minus b times minus b is plus b squared. Remember, minus times minus is plus, right? So I get here plus b squared, and again I can group these two together and I will get a squared minus 2ab plus b squared. And this is exactly where I was supposed to arrive. And then the last one. Here you see that I started actually from the right-hand side, because it would be difficult to start from the left-hand side. Here I simply have parenthesis multiplication, so it is easy. I know how to do this. And this is exactly the same pattern here. First this multiplication, followed by this multiplication, right? So I start by a times a is a squared, then a times b is a b, and then I continue. plus minus b times a, you know, it is simply minus ab, right? And minus b times plus b is minus b squared. And you see here I have a cancellation because I have plus ab and minus ab. So it is the same number added and subtracted. So these two cancel out. And this gives me my left-hand side in this case, a squared minus b squared. So now I'm done proving these three formulas, and now I will move to my presentation. So here, before I show you geometrical interpretation, I would like to tell you that you now know how I knew in video 2 that x squared plus 2x plus 1 is equal to x plus 1 all squared. You see, I simply use this first formula here with a equal to x and with b equal to 1. Then I get x plus 1 all squared is equal to x squared plus twice x times 1, it is simply 2x, plus b squared is equal to 1 squared is equal to 1. So you see, this is what I knew. You maybe didn't know this back then, but now you know how why I was able to replace this expression by this one. And you see here, in the same way you would compute x plus 2 all squared as x squared plus 4x, because here you have to take twice x times 2, it is 4 times x, and b squared is equal to 2 squared is equal to 4. Here, if you get a minus, you just follow the same principle with a double product and the square, but you have to put minus before the double product. And here may be slightly more difficult if you have a fraction here. You simply proceed in the same way, but well, you have to work with fractions, right? So here in this case, your a is equal to x and your b is equal to 1/2. So a squared is equal to x squared. Then you get further twice ab. 2 times 1/2 is 1, so you just get x as the double product, and at the end b squared is equal to 1/4. And why do I show you this? Well, because you will often need to be able to recognize from the right hand side what kind of square you get. So this is why it is kind of good to memorize these examples. This will make your life easier. Okay, now we proceed to the illustration. So I start by this formula. A plus b all squared is equal to this expression, and I will show it with help of squares and areas. So this will also give you a nice illustration of the name of the procedure which we work with, completing the square. So first, of course, this will only be valid for a and b which are positive numbers, but this formula is valid for any real numbers. So we start by taking a square which has a side length a plus b. You see, here is a plus b and here is a plus b. So this is a square. The left-hand side of this formula is the area of this entire square, right? A plus b all squared, because this is how you compute the area of a square. And now, what about the right-hand side? You see, here, this square has area a squared, and this square has area b squared. And then you have still two rectangles, right? Each of them has area a, b. So you see, the right-hand side describes the same area but divided in sub-areas. But still, the sum of these four areas, which is obviously equal to this number, is equal to the entire area. In the same way, you can, but slightly more difficult, you can illustrate this formula. So now I take a large square, a by A. So the side length is A, and I take some B here which is smaller than A. And you see, the left-hand side of my formula is equal to the area of this square, because this square has side length A minus B. So the area is A minus B all squared. And now I have to work for this to show that this area can be expressed in this way. How? Well, A squared is the area of this large square, right? Then I can subtract twice area of a rectangle A times B, so one time, and the second time. And you see what has happened. I have subtracted this area of this here twice. So I have to add it in order to get this area here. And the last formula, A squared minus B squared. This will be illustrated with help of this square here, which is A by A square. And here you see I have prepared some B, which is less than A. And again, both A and B are positive in this example. So A squared is obviously the area of this entire square. And B squared is the area of this square here. So the left-hand side of my formula is equal to the area of this green surface here. So this is my left-hand side. And what about the right-hand side? You see, this yellow rectangle here has area A minus B, because A minus B is this length here, times B, because this is B here. And this rose rectangle has area A minus B, because here is A minus B, times A. And what happens when we put these two areas together? You see, here, this area plus this area, when I add these two products together, I can factor out A minus B here, and in the parentheses I will get A plus B. So this is exactly the right-hand side of my formula. So in this way, the left-hand side, which is the area of this green surface, is equal to the sum of these two. So now you have seen three important formulas, and you have seen geometrical interpretations. Thank you for watching. Bye-bye.